Hi everyone, thank you all for attending this talk, and we're sorry that we couldn't attend the conference in person. To follow along with this video, we've uploaded a PDF copy of our slide in the link that you see here. It also includes a transcript of the audio recording if you want to follow along. Today I want to talk about our work with middle school science students, where we explored the possibility of integrating computational thinking, or CT, in an existing science class. In particular, I'll talk about the value afforded by computing systems to create multiple representation of a science phenomena that we believe can help students dive deeper into learning abstraction and more critically learning through abstraction. Now, educational computing has always been about ideas. These build on theories from Jerome Bruner and Piaget and was brought to the forefront by Seymour Papert, who saw the possibility of computers to be objects to think with. We see the influence of computing as a tool to explore ideas in a line of systems such as Logo, Star Logo, and NetLogo, which is what we used in this project. Related to that, Andy DeSesa introduced Boxer, a system that facilitated learning important ideas of physics as well as computation. Now, in all of this work, we find that the critical value is in providing meaningful context for the students to encounter computing. Such contextualized introduction to computing has been argued for in teaching practices such as Mark Gusdale and Barbara Erickson's media computation system, Caitlin Kelleher's storytelling Alice, and Dennis Kafura and team's BlockPy system at Virginia Tech. Now, I believe that this value is very well reflected in this CS Plus section where we are all seated here today. Now, along this line, computational thinking, or CT, is well aligned to this idea of contextualized introduction. CT is about exploring ideas through a computational medium. Now, although critical ideas can be captured in programming exercises, CT is well positioned by being much more broader than just programming. Now, in our project, we've tried to integrate CT into existing middle school science classes. There are several pragmatic reasons to do so. There's limited room in an already overloaded K-12 curriculum to add a dedicated computing class. Also, many schools have a shortage of teachers and resources to teach dedicated computing classes. More importantly, given that computing skills are increasingly becoming central to the modern workforce, there's a risk of widening inequity if we cannot provide students with rich learning environments that provides them an opportunity to learn fundamental concepts of computing as well as the domain knowledge. Integrating CT can provide such opportunities to students to see and think about an increasingly computational embedded world. Now, this goes back to DeSesa's argument for computational literacy, that is, computing as an infrastructure to understand concepts of varied subjects, including that of computation itself. Now, also from a learning science perspective, integrating CT into classes can open possibilities for deeper engagement and lead to synergistic learning gains. The key there is to find elements of alignment between CT and the domain in which CT is integrated. Now, in our integrated approach where we brought CT into existing science classes, we find that abstraction is one such common element in both the domains. And in this work that I'll talk about today, our focus remains with abstraction. Now, let's unpack abstraction a little bit. When we introduce abstraction to students in computer science, we typically begin by presenting it as a hierarchy. The key skill that students encounter at the beginning is to extract important features, ignore unimportant ones, and then find commonalities across context. Now, a simple example of this is that the way we think about computing systems in general. At the lowest level, we have the electronic states, which can be on or off. Then moving up a ladder of abstraction, we represent those states in a binary form, zeros and ones. Now, a further level above that, one can choose to represent it in a decimal system. For example, in the image that you see here, the binary number 01000001 can be represented as a decimal number 065. Now, a level above that, we can choose to take that decimal number as a representation of text. In this case, 065 translates to the letter A if we follow the ASCII encoding. Now, the takeaway from here is that very rarely beginners working with the letter A have to think about the lower levels such as the electronic states or the binary states. Now, beginners are not introduced to the lateral hierarchy such as abstract data types and the operations and constraints that come with it. These are positioned as more advanced concepts in computer science. Now, whereas when we look at abstraction practices in sciences, we find that students need to think about lateral movements right from the start. Consider a simple chemical equation such as the electrolysis of water, where the equation is written as 2H2O gives 2H2 and O2. That is, two water molecules split into two hydrogen molecules and one oxygen molecule. Now, the equation itself is represented at a molecular level, where we look at molecular transformation with atoms rearranging themselves. Now, in this case, there are 4 hydrogen atoms and 2 oxygen atoms on the left side or the reactant side. And law of conservation of matter dictates that the product side or the right side should also have the same number of atoms. Now, but the concept of conservation of matter and distributive atomic count alone is not enough. For example, one equipped with the conservation of ideas of conservation of matter can ask, why can't the equation simply be H2O splitting into H2 plus O? There are, after all, equal number of atoms on both sides. However, the thing with chemical equation is that it represents several implicit aspects of the chemical phenomena. In this case, it is important for students to understand the energetic states and draw upon the fact that hydrogen and oxygen are diatomic. That is, they typically exist with 2 atoms together. That is H2 and O2. Now, this understanding is essential to be able to grasp molecular level equation at the top. So even though there is some level of hierarchy between atomic and molecular and atomic levels, students need to work with lateral ideas together to understand each of those representations. Now, in middle schools, when we worked with middle school students from Texas and Virginia as part of our study, we observed one particular class of 21 students, and in that unit, students encountered multiple representations of the natural carbon cycle, and it presented several different representations. We presented several different representations in the process. Now, the first was the physical macroscopic phenomena, where students began with a simulation of the view that was quite familiar to them. Now, the simulation particularly showed cows grazing on grass under a bright sunlight. And following that, the instructor led a discussion where the class encountered scientific representation of the phenomena. And this included chemical equations that encapsulated the phenomena that they had encountered earlier. Following the discussion, students were encouraged to explore the simulation further. But this time around, they explored a feature that we had built where microscopic representations of the molecules were overlaid on the macroscopic view, as you can see here. Now, in the figure here, you can see carbon dioxide molecules in the atmosphere, glucose molecules in the plants, and also inside the cow that has eaten some of the grass. After this, the students were then introduced to parts of the code that implemented the simulation. Now, an example of the code can be seen here that implements the plant's photosynthesis process. Now, the introduction to the code was heavily scaffolded with the help of the instructor. We'd written the code in such a way to scaffold encounter in a way that some of it does not follow typical software engineering guidelines. Now, the code was verbose, repetitive so as to facilitate easy exploration and navigation, and was ordered to make it easier for students to get a higher level understanding of science before diving deeper into the computational mechanics behind it. In that sense, we prioritized learning science over writing efficient programs. Now, it is worth noting here that all of the computational representations that we presented to the students were interactive and highly modifiable, and students were encouraged to explore and modify those representations. Now, in the class of 21 students, we observed that there was gap in their knowledge. Now, for example, we would ask students if H2 plus O2 equals H2O was a balanced equation or not. 11 of the 19 students who responded in the class correctly mentioned that the equation violated conservation of matter. However, 8 of the 11 who correctly responded struggled to balance the equation correctly, saying things like that would be H2O2 or it should be H2O plus H2 plus O equals to H2O. Now, it became clear that while students were familiar with the principle of conservation of matter, they had not yet imbibed the concepts of energetic states and molecular structure that is implicitly summarized in the chemical equation. Now, the implicit aspects of those equations became explicit when the students worked on the code. Code requires statements that explicitly mention the change in state. The transformation of atoms from the reactant side to the product side is implicit when students encounter chemical equation, whereas it is not so when students encounter the code. What we observed was that students were not able to draw from their science understanding to make sense of the explicit code statement. That is, they were not able to move laterally between different representations. Now, for example, when a group of students, when encountering the photosynthesis function, encountered the statement set plant water level minus 6, they grappled with the mechanics of the statement. The group interpreted it simply as water level minus 6, which is a notion associated with abstraction that is quite common in computing. They could not see the science that was embodied within the statement. Now, as the sessions progressed, with the instructor's scaffold, students increasingly began to connect the science concepts with the code representation. For the same group, we saw a movement where we increasingly saw the students where they moved from statements like the water level goes down 6 to takes water from the plant to finally seeing that the entire code as a unit represented photosynthesis. Now, the students here moved laterally between different representations, connecting via abstraction-based thoughts to develop a new understanding where they could see the code representing the science within itself. Now, to summarize this observation, in computing, we want students to learn to abstract. We see this in programming exercises such as in generalizing class structures and thinking about class relationships. What we find in our study is that when students encounter multiple representations, such as with the macroscopic representations of the thing that they see in their day-to-day life, which is then explained through a scientific representation such as a chemical equation, and further deepened by presenting modifiable and interactive representation through the computers, students have to move laterally across representations, abstract key features from each of those encounters, and build upon their understanding to make sense of the new representation. This is what we saw when students moved from the mechanics of the code with the initial water level statement to realize the embodied science of the code at a higher level, which they eventually did with the instructor's support. That is, students were able to learn through the abstraction. Now, these two differences between learning to abstract and learning through abstraction are quite analogous to how students begin by learning to read and then start to progress where they start reading to learn. Here too, we argue that students initially learn to abstract, but with careful design and carefully placed scaffolds, students can move further where they can learn through the abstraction. This is in sum what we argue in the paper. Seeing the code as being part of a single unit requires lateral movements. Now, from a computing perspective, that is part of procedural abstraction, which is quite critical in practices like modularizing and reusing code. Now, but then this may not necessarily work hand in hand. Now, focusing on hierarchies does not necessarily create encounters with lateral abstraction, which is what we discussed with the binary, decimal, and text example earlier. But similarly, focusing on lateral abstraction alone may not be sufficient for the students to grasp ideas of hierarchical abstraction. This, we believe, is a limitation of the work and requires further exploration. Now, reflecting on our experience, we recommend the following 5 practices to promote students' deep engagement with abstraction and learning through abstraction. First, we believe that presenting the multiple representation in context was beneficial for the students to move between representation and draw upon their earlier understanding. The students were familiar with some aspects, and the familiarity supported in seeing how it could be expressed or represented in different ways when they encountered the newer representation. Now, we firmly believe that technology is a tool and that it can be used to facilitate the teaching process. But that can only be done if the instructors find it to be of value in furthering their pedagogical practice. Now, so the design of the representations have to closely follow the pedagogical goals. Now, for example, in our case, the photosynthesis function emphasized exactly the pedagogical point that the instructor wanted to make, and that afforded opportunity for the instructor to scaffold students' encounter with the newer representations. Third, we believe that it is critical to order the students' encounter with different representations, beginning from representations that the students were familiar with, allowed the students to draw upon their understanding when they encountered the newer representations. The need for ordering representations has been argued in prior learning science literature, particularly in the brilliant work by Sharon Ainsworth. Now, related to the ordering of representations, we believe that ensuring that the representations were coherent can help students transition between the representations. Now, in our case, the students were able to see similarity and notice the differences that arose when they encountered newer representations. For example, students were able to connect the overlaid representation of the glucose molecule in the plants to the plant glucose level variable that they encountered in the photosynthesis code. Finally, we argue that there is a need to allow for friction to occur in the students' discussions when they encounter different representations. Now, in our case, this was most prominently seen when the students encountered things that were implicit in the chemical equation, which was then seen explicitly in the code. Building on the importance of students' struggle in learning concepts, such as with Piaget's assimilation and accommodation, we believe that the friction that occurred encouraged students to draw upon their understanding of the phenomena from other representations that they had encountered earlier and negotiate it with the elements in the new one once they encountered the newer representation. Now, we argue that focusing on learning through abstraction promotes deeper engagement with both the critical ideas within computing as well as the domain knowledge. More broadly, the focus on learning through abstraction re-emphasizes the need for students to be introduced to computing through meaningful context. Further, it emphasizes the value of computing as a tool, one that promotes deep engagement with ideas of other domains. we're really sad that we couldn't be here to answer any questions that you have or to take this discussion further. But if you feel like it, please feel free to send us an email to continue this conversation. Thank you.